What did we cover this month? Well, let's go real quickly on the recap. Here it is. Okay, we have this. We have these gentlemen throughout history, and all the way from Galileo to Mr. Stephen Hawking. And all these people came up with all these ideas that we have known as mathematical physics. And what is mathematical physics? Well, it's irrational explanations. That's all we see. They say, well, we got all these equations. Look at the technology we have. Yeah, that's got nothing to do with science. Technology and science are two different disciplines, branches, whatever. Technology is not even a part of science. Science, rational explanations. That's what science is. People want to know how this universe works. And if we're going to become extinct very soon, hopefully we all die at least understanding how this universe works. Then we can all go to bed. Okay, but right now, most people in the world believe these folks, and what they have is irrational explanations of how this universe works. Okay, and so we covered what? The differences between math and biz. Okay, in mathematics, they talk about distance, but it's not distance, known as distance traveled. Distance traveled is not the same thing as distance. Distance belongs exclusively to physics. Distance traveled belongs exclusively to math. So when you look at the equations of force, okay, that supposedly Newton came up with, obviously, like I said the other day, there were ideas even before Newton on these issues. But for the sake of argument, we're going to assign them to Newton so that we can at least use his name. We have his second law, force equals mass times acceleration, and it's not equal to the gravitational equation, which is force equals the gravitational constant g, mass 1, mass 2, divided by distance squared. And they're not equal. The mathematicians constantly put them as equal because they play around with the numbers, but they don't play around with the qualitative notions that underlie these two equations. What's the difference? Well, again, distance traveled is what you have in the force equals mass times acceleration. That acceleration it has to do with distance traveled. Distance traveled by one object. That object starts at a given point, moves forward, they look at how much it traveled, how many meters, they put 1 meter after another, they count meter or unroll the measuring tape and they say 3 meters, okay, and that's a value they're going to put in there. That distance traveled is the distance traveled by the tip of your measuring tape. Okay, so we're looking at the unrolling of your measuring tape, and that measuring tape, the tip of your measuring tape, traveled from point A to point B, 3 meters. Distance traveled by one object, the tip of your measuring tape. That's different than what you see in the gravitational equation. That distance squared there is separation between mass 1 and mass 2. That distance is not the same distance traveled as the second law, force equals mass times acceleration. One is dynamic, the other one is a static concept. Then Newton's second law there, it's an equation of push because the object is moving from point A to point B. On the other hand, the other one, gravity, we called it pull, the pull of gravity, but actually it's tension. What you have is tension because all you're looking at is the separation between two objects. Nothing is moving because you just want to calculate one value. And so conceptually, what you have separation between two objects, and at that point they're just static, nothing's moving, we call that tension. And tension is not a force. Tension does not meet the definition of the word force. What is force? Well, it's got to have motion. And tension is the opposite. It's a static concept. Tension means there. It's like two objects separated by a stick made of a single piece. That's what tension is. And say, well, but we're pulling. Okay, so, here we have a rubber band. Let me get a smaller one here. Here we have a rubber band. And I'm going to pull it to max. Well, it's not max, but I don't want to rip it. But let's say I'm pulling it completely to max. And it can't move anymore in any direction. Well, at that point in time, there is no force. It's not moving this way, it's not moving that way, and force requires that someone win the tug of war. Right now, no one's winning the tug of war. This thing is stretched to max. That's called tension. Tension is like if the two objects were separated by a stick made of a single piece. That's tension, and that's Newton's gravitational equation. Then, we play around with those, and we put force divided by acceleration. That gives us mass in the second law, right? But mass is equal to weight. And the mathematicians say, well, it's not true. Mass is not weight. Weight is not mass. They're two different things. Well, are they? That looks to me like they're the same because the mathematicians use the word mass to refer to weight. What are they talking about? They're saying, well, if an object increases in speed against, or the pressure, right, against the scale, they call that mass. Wasn't it Einstein who said that? Object travels at near the speed of light, and as it travels faster and faster and faster, its mass increases. So what are you saying? That it gained more atoms? Is that what Einstein was saying? It becomes fatter because suddenly, it's gaining more atoms in it. Here you're traveling at almost the speed of light, and you're traveling faster and faster and faster. You're gaining more mass. What do you mean, more atoms? Or is it that you're pressing against the scale with a greater pressure? Well, if you're doing that, then you're doing weight. You're not doing mass. But they call it mass. That's the issue there. And moving on, work. What is work? Well, work, if you just do it on a horizontal plane, we said that's just force times acceleration. But then if you're going to go on an inclined plane, now you're going to have to factor gravity in there. And instead of looking at what happens in physics, which is factoring gravity, whatever gravity is, right, physically, instead of factoring that, they said, oh, we solve this very easily. We just take the cosine of the angle, and depending on the angle that you have for that inclined plane, and we calculate it. Well, that's okay in mathematics. What does that tell me about physics? In physics, we need to know the cause. Why suddenly it's become harder to push the ball upstream than it was rolling it on a horizontal plane. And for that, you have to factor gravity. And they don't do that. They just do a calculation based on cosine of A, and we're done. That's how they calculate it. Yeah, and the calculation is correct. No, we're not arguing against that. We're saying we don't understand the physics. Why did it suddenly become harder to push that ball up the inclined plane? And they say, well, because we have cosine of A. Well, that's not a reason. That's a description. That's an equation. You haven't told me the cause, the physical cause. Okay? Energy. Oh, the big word energy. Biggest word in mathematical physics. Whenever you're very ignorant, you don't know something, just say energy and you're done with. It's like in old religions, the traditional religions, they would say the spirit did it. Oh, okay. We all understood that because why did the curtain move? Well, the spirit moved it. And, the spirit flies, the spirit moves the air, all that stuff is done by the spirit. And energy is a spirit of mathematics. Whenever you don't know something, just use the word energy and you're done. Because everybody says, oh, now I understand. Did you? Because they define it as the capacity, which is a concept. Capacity is a concept. There is no physical standalone object called capacity. Please draw it, put it in front of me, get some clay and mold it, and I want to know what capacity looks like. And no, you can't do that. But they treat it as an object. They say we transferred energy. What do you mean you transferred it? What is this? And they say, well, it's a figure of speech. You don't have to take it literally. In physics, we take the explanation, the mechanism, literally. Now, if you want to use, parables or whatever for your closing arguments, that's just fine. You want to use poetry, that's great. No problem. But the meat of your theory, your explanation, your mechanism had better be literal. Okay? That's the way it works in science. And no, these people use that parable, that figure of speech, whatever you want to call it. That's what they use to give their explanations. And when you put them against the wall, when you begin pounding them at the corner, they say, well, that's not physics anyways, that's philosophy. And so why did you even attempt to do philosophy if it's not part of your discipline? If your discipline known as mathematical physics has to do with descriptions, mathematical descriptions, predictions, observations, measurement, whatever you want to call all that nonsense, if it's got to do with all that, why did you even attempt to give a physical interpretation to your equation if the physical interpretation is irrational? And when I put you against the wall and begin pounding you, you say, well, that's philosophy anyways. Why did you try to do philosophy? You should have stuck to doing your math, and there wouldn't be a fight. We have a fight because you're claiming that you understand something about the physical world, and you're giving me an equation, giving me an irrational explanation, and when I call your bluff, you say, well, that's philosophy anyways. We don't do that. We have no way of proving it. That's non-scientific anyways. That's what you get today. Okay, and we covered then the pendulum, the last part that I covered the other day. And none of these folks, from Galileo all the way to good old Stephen Hawking, none of these people ever discovered the mechanism. They do have the equations. They can tell you that to the last decimal point. Great. They still don't know why a pendulum moves like that, okay? And yeah, we do, and here it is, okay, here's the explanation. Every atom of the pendulum is tied, bound, physically bound to every atom on Earth. We only show those ropes that are bound to the center of the earth, because that's where all the ropes are converging upon. So the pull, you could say, is towards the center of the earth. Okay, and that's what moves the pendulum. And all these people, all these great mathematicians, the reason they never figured this out is they said, well, I don't see any rope. I can't touch any rope. What are you talking about, Bill? I mean, where are these ropes? I don't see them. And so we have to begin at square one, and we do it with a little pencil. Don't ever do this experiment at home, okay, unless you are in the presence of a relativist, okay, because it's a very dangerous experiment. And we let go of the pencil, and it falls to the center of the earth, really to the floor, to my table in this case, okay? Let's do it again. You got to do it repeatable. Otherwise, it's not scientific, they say. Okay, so we repeat it. That's part of the scientific method of the mathematicians. And there it is, okay? It fell 2 times to the ground. Now, why didn't it fall to the ceiling? That's what we want to know. That's what we want to understand. And yeah, you can see, or better, the opposite, you can't see. You don't see anything here, you don't see anything here. And so if there's nothing here and there's nothing here other than air, and we know that air is not the one that's causing this, because we can do this in outer space when there is no air, or on the moon as they did it, we can drop, for those who believe that we went to the moon. Got to specify that. Okay, there's nothing here, nothing there. So what pushed it? What pushed the pencil downwards? What pulled it? That's what you got to explain. And you say, well, I can't see or touch anything other than air, right? And yeah, what that tells us is that there is something that came in contact with the skin of the pen that we can't see or touch. So we're not going to be figuring this out by running experiments, because we cannot see or touch the mediators of gravity. Okay? And that's what they missed all these years. So we come in there and we say, well, if you're going to make this phenomenon rational, you had better put some physical entities here somewhere. And a lot of people put particles. They said particles are pushing down on the pen. Well, that's irrational for many reasons. What we say here is that every atom of the pen is bound to every atom on Earth. Okay? So every atom of the pen is bound to every atom on Earth. And so when we let go of it, it drifts in that direction, because as it falls, because that's the direction in which all the ropes are essentially directed, as it falls, the ropes fan out, and the angles become greater and greater, and more independent ropes act with on the pen, and that's why the pen falls downwards. And there are fewer ropes connected towards the ceiling and to the stars and whatever. So yeah, because of distance, not distance traveled, but because of distance, a separation between the center of the earth and the pen tends to go in that direction, accelerates downwards. Oh, and again, it's an acceleration. It increases. Why? Because the ropes are fanning out as this thing falls closer and closer to the center of the earth. It also shows why the earth is a sphere and not a little pancake, as the flat earthers say. Okay, the pancake earth. That's what they believe in. Okay, and here's another fellow says, we measure mass by putting it on a scale. No, we don't measure mass, because mass is the quantity of matter, meaning you're going to count apples. That's what mass is, counting apples. So you have to say 10 apples. And so you don't measure mass, you count units of mass, and you should state your answers in terms of those units. You can say, this has a mass of 1 gazillion atoms, for example, or units of mass, whatever. Then we would understand. That would be the way to state quantity of matter. So we do not measure and give you a value in kilograms, because that's known as weight. Okay? So it's called weight. Mass, you count units. Okay? So this guy insists. He says, the word mass has 2 meanings in special relativity. Well, he doesn't say that, by the way. This I get from the Wikipedia. Okay, just to show where this guy stands. It says the word mass has 2 meanings in special relativity. Rest mass is an invariant quantity. What are they talking about? Quantity of matter. In other words, mass. And then relativistic mass is independent, or is dependent on velocity. What are they talking about? They're talking about weight, because now you're talking about how much pressure you're causing, on the scale. So relativistic mass is not mass. They can call it relativistic weight if they want, but that's not mass. And this is where we get into circular arguments, because these people say it's mass and they're not mass. They're talking about weight. And so, the question is, did the object accumulate more atoms, meaning quantity of matter, or did the object increase pressure against the scale, which is weight? So again, yeah, it is that they confuse the word mass with weight. They don't like to talk about weight because they know that weight varies according to where you measure. For example, if you measure on the moon, the ball is going to weigh a little less, right? About a sixth less. And so, or a sixth of what it weighs here on Earth. But this, what does this tell us? They're telling us that the mass remains the same. What do you mean the mass remains the same? How do you determine mass? You weigh it. There you say, you put it on a scale. That's how you determine mass. And yeah, if you're going to determine mass by putting it on a scale, then you're doing weight. And so, again, they're chasing their tails around. They're saying mass is weight, weight is mass. They're calling weight mass. And they just drive you nuts because they just go around in circles. So this fellow continues. He says, well, here, he says, to calculate number of atoms in a sample, divide its mass measurement in grams by the AMU, atomic mass unit, right, from the periodic table. Then multiply the result by Avogadro's number, 6 times 10 to the 23rd. Okay, so that's to calculate atoms. Then you should state mass in terms of quantity of atoms, okay? That's what you should do. You can't state it in terms of kilograms because that's not what you just said. What you said is, we weigh it and then we turn it, using Avogadro's number, we turn it into quantity of atoms. Great, I have no problem with it. Then state your mass in terms of atoms. Don't state it in terms of kilograms. Kilograms, weight. They say, no, that's measured in newtons. Nobody uses newton. Nobody says, I weigh 500 newtons. Nobody says that, okay? Everybody says, I weigh 500 pounds or whatever. That's what they'll say. Nobody uses newtons. They use pounds and kilograms for weight. And they say, well, but that's mass. No, because you defined it as quantity of atoms, as quantity of matter. And there, if you have a way of calculating it, great. That's even more power to you. Give your answer in terms of quantity of atoms or units of mass or whatever you want to call it. That's the way it works. Okay. So, yeah, big confusion with mass and weight. A lot of people just recite what they learned by rote in high school or college. And here we correct them. We set them straight, okay? And when they don't understand, we use the bgaede way. we teach them the bgaede way, okay? Baseball bat therapy. Another fellow says, if the mass of an object is meant to be equivalent to the number of atoms, yeah, then how can an elementary particle have mass since there is nothing there to count? What do you mean there's nothing there to count? You have there one elementary particle, fundamental particle, and we have one unit of mass. That is your unit of mass. Let me tell you what the problem is. The problem here is that the mathematicians, especially the quantum mathematicians, the mechanics, right? What they say is, oh, we have an elementary particle. We have a fundamental particle. For example, the electron, or maybe the gluon, or one of those, right? And they'll say that's an elementary particle, photon, okay? What do they mean by that? It's a particle that's indivisible, made of a single piece. Is that the notion they're trying to convey to you? Made of a single piece, indivisible, that it has no internal structure, whichever way they want to phrase it, no problem. But what happens? The reporter at the end of the room, he says, what is it made of? And that's when they run into trouble, because what these people answer, they should have said, well, elementary particle, fundamental particle, by definition, is one that's not made of anything. That's not what they answer. What they answer, they say, well, give us more money, and we'll build a bigger collider, one that has the radius or the orbit of Pluto. We'll smash it, and we'll tell you what it's made out of. That's what they answer. And so, yeah, they go out there and they give them more money, and they say, okay, now we have the CERN, the LHC. Okay, great. And they go in there and they smash this alleged particle, this indivisible, and they smash it and they say, okay, the alpha particle is made out of betas. And so they give the presentation to the world, we found the beta. And the reporter at the end of the room says, what is it made out of? Say, okay, give us more money. We'll build a bigger collider as big as the galaxy. We'll smash it and we'll tell you what beta is made out of. And so quantum mechanics is one of those things that is eternal. It gives them job security forever because they just say, well, it's an elementary particle. And when they say, what is it made out of? They say, give us more money and we'll tell you. And so that here they are always smashing what they think are particles. They think they're smashing them, crashing one against the other and getting all this debris and giving them names. They get Nobel Prizes for this. They say, okay, I found a little bit of the alpha particle. Now I got the beta particle. Okay, and then the delta and the gamma and whatever. And so we have the gamma particle. What is the gamma made of? Well, give us more money and we'll smash it and we'll tell you what it is. And the money keeps rolling and they keep giving you this runaround. And see, we have a problem because you would think that quantum mechanics, ultimately, conceptually, not a question of running experiments, conceptually should have a fundamental particle that makes up everything else. And this should be a hypothetical particle. You don't have to see it. You don't have to go to a lab and say, let me detect it. No, none of that. From a conceptual point of view, there should be an ultimate particle because you can't divide the ultimate particle and end up with nothing. Okay? Because that ultimate particle should make up everything else. That should be their starting point from a conceptual point of view that underlies quantum mechanics. You understand what I'm saying? I'm saying there has to be the buck has to stop there somewhere. And they don't do it that way. They go the other way around. They say, well, we smash particles and we give them fancy names, get Nobel Prizes, and if you want to know what that particle is made out of, give us more money. And we'll smash that one too. But that doesn't give us the conceptual foundation for quantum mechanics. Conceptual foundation should be, there should be an ultimate particle. We'll call it the Z particle. Fine. You can't break up Z, it's the ultimate particle. And that makes up everything else. Now present your theory to me. Present your entire theory based on that fundamental elementary particle. And they don't do it that way, because they would be dead in the water if they did it that way. That would be the end of quantum mechanics, because now we reach the end of the line. So, well, for the next million years, we're going to be smashing particles, trying to get the next level particle? Is that what it is?